All right, for the online students, we're just working on this worksheet here. This worksheet is going over pixel size, voxel size, scan time, and signal. I'm going to pause the video as the students work on it for about 10 minutes, and then we'll review it here in a little bit. All right, so we're back from a little bit of break. Students have been working on this worksheet for a little bit, but now we are going to review it. So let's start with question 1 here. So in a fast spin echo sequence with these parameters, what would the scan time be? So the most important thing to set yourself up for success is choosing the right equation to use first, and then selecting the parameters that are necessary for that equation, and then just ignoring all the rest. All right? So let's go ahead and write out our scan time equation for number 1. What is that going to be? TR times phase encoding steps times next. Okay? But look at what we're dealing with. We're dealing with a fast spin echo pulse sequence. So we have to now incorporate our echo train. So this is the equation we should be using. Okay? Now let's highlight the parameters that are necessary. So here's your PE. Your phase encoding direction is always going to be the smaller number. Because remember, you want to have the shorter axis of the matrix going with the phase encoding direction because you want the scan time to be as little as possible, and you don't want that phase wrap to happen. So 224 is going to be your phase encoding. TR, pretty basic, it's right there. TR is 2500. Your next is 4. You can also see it as NSA, remember, number of signal averages. And then your echo train length is 12. Okay? So now let's calculate that. So start with our TR. So we have 2500 times 224 for our phase encoding direction times 4. Let's equal that out. It's a big number. It's in million, 2 million plus. But we have to divide it by our echo train length, which reduces our scan time because we fill 12 lines of K-space per TR. So divide that entire number by 12. Okay, this is the number we get, but this is in milliseconds. 186,666 with a running decimal. So we first have to divide it by 1,000 to get it into seconds. So here is our answer in seconds, but that's not how the registry likes to have your final answer. They're not ever going to have your final answer just be plain seconds, 186 seconds, because nobody really knows what that is, right? If you had to think about how many minutes is that, I don't know. So to get it in minutes, you have to divide it by 60. So here we go. So now we have 3 minutes, 0.11. But that 0.11 is still in minutes. So this is not your final answer. You still need one more step. And this is where the registry will get you. They'll put on the registry, they'll say 3 minutes and 11 seconds. And that will be the one you'll want to select because you did all that work, but there was one more step to do. So the answer is going to be 3 minutes, but now we got to convert this 0.11 back to seconds. So do 0.11 times 60. And now we get 3 minutes and 6.6 seconds. Okay? 3 minutes and 6.6 seconds. They are evil. You did all that work. You found the right parameters. You used the right equation. But you just forgot to do that last step to go from minutes to seconds. 3 minutes and 6.6 seconds. All right. Let's go on to the next one. All right, what's the scan time equation for the next one? It says, what would the scan time be for a 3D volume acquisition? So what are we going to use?
TR times phase.
3 minutes and 6.6 seconds.
Okay, TR times phase matrix. I heard you say, Jasmine.
Times NSA divided to NEX times numbers like
Good. So that last little bit, times number of slices. Okay? So instead of dividing it by our echo train length, that last part of the equation is a little different. We have to multiply it by the number of slices. So once again, let's highlight the parameters we need. So TR, 24 milliseconds. We don't need TE, we don't need flip angle, we don't need field of view. Slice thickness, remember that's where they're going to try and trick you again. We don't need slice thickness, we need number of slices. We have 76 slices. Our phase encoding is the smaller number of the matrix, 176, and then our next is just 1. Okay, so those are the 4 parameters we need to use. So let's get our calculator back up and do this math. So 24 times 176 times 1, because there's only 1 next. That comes to 4,224. But we have to multiply that by the number of slices. So times 76 slices. Okay. So that's your answer in milliseconds. So let's go ahead and divide it by 1,000. Get it in seconds. And then divide that by 60 to get it into minutes. So we have 5 minutes and some change. So right, 5 minutes, but then now we have to convert this 0.35 back to seconds. So let's clear this. So it's 0.35 times 60, 21 seconds. 5 minutes and 21 seconds is the answer for number 2. Yeah.
Oh, here's the NSA.
NSA is the same thing as
the same
next.
thing. Okay,
Yep.
Yep.
It's just how the manufacturer, whatever manufacturer you're using.
Wait a minute. So we do. Okay. How did we get the highlights again?
You multiply 24 times 176 times 1 times 76. Okay, so you got that number. So once again, 24 times 176 times 1 times 76. Divide that number by 1,000. This is the hardest part, to remember the steps. Divide the number by 1,000. It gives you seconds. But now we have to get it in minutes. So divide that by 60. 5 minutes and some change. But this 0.35 is not the seconds. It's still in minutes. So 5 minutes, and so let's take that 0.35 and times that by 60 to get it back in seconds. So we have 5 minutes and 21 seconds.
One more question. So after we divide it into 1,000, I get 321.024, and then you said times it.
Times whatever's past the decimal by 60.
The 0 to
Whatever's behind the decimal by 60.
like we did the last time.
Okay, we're going to do one more here so that you get the hang of it. All right, so what's our scan time equation for the next one? TR times phase encoding times next. Good, because this is a 2D acquisition, which is it's just a spin echo. So if they don't specify whether it's 3D or 2D, assume it's going to be a 2D acquisition. This is a spin echo. It's not fast spin echo, so we don't need to worry about our echo train length. Okay, so let's highlight the parameters we need. So TR is 3,000. Our phase encoding is going to be the 280. It's a smaller number. And our next is, once again, is 1. Okay? So let's do that calculation. So we have 3,000 times 280 times 1. Okay, we get 840,000. So then divide that by 1,000. And that's in milliseconds now. So now we need to get it in minutes. So do we divide that by 60? It should be 14 minutes flat. 14 minutes flat. Okay? And if it's not a whole number, remember, whatever's behind the decimal, you have to multiply it by 60. So number 3 is 14 minutes flat, and we would never have a whole sequence that was 14 minutes, right?
Oh, okay.
Okay. So I'm going to move on to number 4. Everybody okay with scan time equations? The hardest part is going from milliseconds to minutes, and then whatever's behind the decimal point in minutes, converting it back to seconds. Okay? All right, number 4. This is kind of a trick question. Changing the size of the voxel in the frequency direction will have blank effect on scan time. So do you see anything on here that says frequency encoding direction on any of these equations? Exactly. So no effect on scan time. Because you're only incorporating the phase encoding within the scan time equation. Increasing, number 5, increasing the number of slices in a 2D acquisition. I should have put on here, we'll do what to scan time. And you're here on question number 2, here's your 3D scan time equation. So you do TR times phase encoding times next times number of slices. But in your 2D acquisition, which is this equation right here, you don't even have to worry about number of slices. So increasing the number of slices, once again, will have no effect. This is where the registry will try and trip you up. All right, number 6, reducing the field of view by a factor of 2 will reduce the voxel volume by a factor of, what's the answer there? 4, because remember, field of view is both sides. So you're dealing with both sides, the height and the width of that voxel. Number 7, reducing the field of view by half, 40 centimeters to 20 centimeters, will reduce 4.0 SNR to what?
1.
Exactly, because here that factor of 4 again. The final answer is going to be 1.0 SNR. So if you reduce your field of view by half, your SNR will drop down by a factor of 4. All right, number 8. Calculate the pixel area for the following sequences. So once again, what should your answer be in? What's your unit? Millimeters, millimeters squared, or millimeters cubed?
Millimeters squared.
Good. So you see pixel area, you know your answer should be in millimeters squared. Okay? So we have to do it for the phase and the frequency side. So our equation is going to look like this. So we first have to convert field of view from centimeters to millimeters. That's an easy conversion. You just multiply it by 10. So now we have 360. And we have to divide that by our phase direction. So 360 divided by 408. And then now we have to multiply that by 360 divided by 512. So you have to do it for both the phase and the frequency direction. Anybody have that number?
Quick question.
Yeah.
So on the formula study guide for pixel area, it says just multiply the phase pixel size times the frequency pixel size. It doesn't say anything about field of view.
Well, that's how, they're skipping one step. The phase pixel size is field of view divided by the number of phase encoding steps. So they're just kind of reducing that down into a simpler version.
I got 0.62.
Okay, so yeah, let's do that. So,
I got-
oh, sorry. Let's take it off there. So 360 divided by 408 times 360 divided by 512. 0.62, is that what you guys got?
Yeah.
Millimeters squared. So once again, your answer has to be in millimeters squared. 0.62 millimeter squared. Okay, final answer. All right, the next one, voxel volume. So what's our answer going to be in?
Cube.
Cubed. Perfect. So the only thing we have to add on to this is our slice thickness. So once again, let's do the quick conversion of field of view in 24 centimeters to millimeters. So we have 240 divided by 272 times, once again, 240 divided by 320. And then you multiply that by our slice thickness, which is 3 millimeters. So give you guys a second to calculate that. 272 times 240 divided by 3 times 3. Is that what everybody got? 1.99. Our answer should be 1.99 millimeters cubed. All right, number 10. So choose the correct slice thickness to create an isotropic voxel. So remember, isotropic means that we're equal on all sides, right? So our phase, our frequency encoding direction, and our slice thickness have to all be the same size, same millimeter thickness. Okay? So how do you think you would solve this? That's my first question. What is the quickest way to solve this question?
Matrix size, same number.
What's that?
Just look at the matrix and it's the same number as.
So the matrix number is the same, but remember that's just the pixel dimensions. So you have to think about how to get the size of just your frequency and your phase direction.
Calculate pixel size.
Exactly. So calculate pixel size. So to find that, just be 240 divided by 272. Divided by 272. What do we get there? 0.88 millimeters. And once again, the answer should be in millimeters because you're only getting one dimension, your slice thickness. So this is the equation you should be thinking about when you're thinking about isotropic voxels. An isotropic voxel is represented by this equation right here. Field of view divided by our phase encoding equals our field of view divided by our frequency encoding, which also equals our slice thickness. So an isotropic voxel is represented by that equation. But if you're calculating for an isotropic voxel, all you have to do is just remove the equal sign and just put a multiplication sign.
What are the multiplication signs again? Why are we doing the multiplication again?
That's just to calculate a voxel volume.
Oh.
Yeah, but I was just saying the first equation above it is what represents an isotropic voxel, because everything is equal on all sides. All right, last one. The smallest object that can be resolved in an image acquired with these parameters. So the smallest object, just think pixel size. So these are just the different ways they're going to be wording it on the registry. So smallest object, once again, we just do the same calculation. So the answer should be the same because we have the same parameters. So it should be 0.88 millimeters. Because we take the 240 divided by 272, which equals 0.88 millimeters. Okay. So I have posted online the answers to this, and it gives you a quick rundown of how to get those answers. So here it says, here's the scan time formula, TR times phase matrix times next divided by echo train length, but then they say, remember to divide by 1,000, and then once again divide by 60, and then whatever's after the decimal point multiply by 60. So this is a good review of what we just went over, but I have posted this on Canvas that you can print out and use that as a review. Okay. Any questions from that? Make sure to practice those because you're going to see some on the not only on my test but on the registry scan time and pixel and voxel volume questions. All right, so now let's grab this document here.
Maybe he has one. Same with you.
All right, let's get back to our original seats. Just
kidding.
So I gave you guys a printout of this document, so it's a little better quality, but I'll plug in the things that are missing up here. This just says image quality. So when we're dealing with parameters, the second part of this chapter is named trade-offs, because we're constantly balancing scan time, our signal, and our spatial resolution. Usually when our signal goes up, our spatial resolution goes down. And sometimes our scan time has to be adjusted depending on the patient, whether they can hold their breath or not, whether they're in pain or not. So you have to be able to adjust these things and think critically of how we manipulate these parameters to get the best image quality for that type of patient. So with this, I also want to add on, usually when we talk about signal to noise resolution, we also have to consider contrast. Just put that right next to it. So some people like to add that into the balancing of the equation here, but when we talk about SNR, you kind of incorporate contrast and noise also. But it's really a balance between those 3 or 4 things, but I like to consider just 3 things we're constantly balancing, because contrast and noise, it looks good. We have bright tissues, we have dark tissues, but we really need good signal. So up here, the first thing we need to talk about is signal to noise resolution. And then we'll compare it to contrast to noise resolution. Okay? So signal to noise, if you look at your scanner, usually you'll have 1.00, meaning you have 100% signal coming from your patient. And you want it to maintain around that 100%. You want good signal for your images. So that's something that can actually be measured. So as we adjust these parameters, our signal, you're going to notice, goes up and down. But remember, our radiologist wants really good signal because we don't want a really grainy image. Just like with X-ray, you want a lot of those photons hitting your image receptor, right? Otherwise, you wouldn't get an X-ray. We need good signals to get a good MRI image. When we're talking about T2 weighted images, our signal goes down on T2 weighted images because our TE is longer. So we have a long TE when we're dealing with T2 weighted images. So our signal goes down. If you break down SNR, what it means is signal to noise ratio. Most of the time we're going to be able to adjust or manipulate our signal, but our noise is random and it's coming from our patient, and that's something we can't really control. So what we want to do is increase our signal and try and minimize the noise coming from the patient as best as possible. But our noise is random, it's constant, but we can adjust and increase and decrease our signal. And like I said, a grainy image is when SNR is inadequate. So if you have what you call like a quantum model image on X-ray, if you have a grainy image on MRI, you do not have enough signal coming from that patient. Whether your coil is not turned on, whether your patient's too far away from that coil, whether you have slices that are too thin, our resolution's too high, so we're not getting enough signal from that patient. All right, now let's compare that to contrast to noise ratio. So this cannot be measured. There's no number associated with contrast to noise. You either see it good, you have good contrast to noise, or you have bad contrast to noise. There's no actual number associated with contrast to noise ratio. There's no 100%, 0%. It's just either I can see that pathology good, it's very bright on my image, or it's very dark on my image. It's harder to see. So that's why on a T2 weighted image, where fluid is bright, we have very high contrast to noise ratio. And a lot of times, pathology is associated with fluid. The definition of contrast to noise is adjacent tissues with different SNR. That's basically the quickest, kind of just easiest way to break down what contrast to noise resolution ratio means. All the parameters of SNR affect CNR except resolution parameters. So what are those resolution parameters? What determines voxel size? There's only three things. So how do you get your pixel size? Good. So field of view, matrix, and one other thing. Like thickness. And that's dealing with voxel. So those are the only three things that deal with resolution parameters. So CNR has all the same parameters except for these three things. So SNR, you have a grainy image when it's inadequate. But when it comes to CNR, the ability to visualize the effect of adequate image contrast and SNR collection. So not only we're dealing with image SNR collection, but we're dealing with image contrast. Dealing with, is it a T2 weighted? Is it T1 weighted? So you have to add not only SNR, but image contrast into the equation. All right, I drew two voxels here. We have a smaller voxel and a larger voxel. And I just wanted to remind you, signal comes from our patient. Remember, we're really just dealing with all those hydrogen proton spins within our body. So if we have areas like bone, muscle, fat, all those areas have a lot of those hydrogen protons within them. Compared to structures like cortical bone, lungs, those areas do not have as many hydrogen spins, so you're not going to get as much signal from those areas. So sometimes you have to increase your voxel size to incorporate more of those hydrogen spins. So signal really depends on the size of your voxel and the tissue you're scanning. So if you're scanning it with a smaller voxel, maybe you're only able to incorporate one of those hydrogen spins. Obviously, that's not a true representation of what's going on. You get more than that, but just for this comparison reason, maybe we only have one hydrogen spin within this tiny voxel. But then we increase our voxel size. Now we're able to get 8 of those hydrogen spins. So we get more signal from a larger voxel. So if we get more magnetization from those tissues, we're going to get more signal. So as our signal increases with this larger voxel, what happens to our resolution? Decreases. So that's where that trade-off comes from, right? Where if our signal increases, usually our resolution goes down as a counterbalance. So if you see something on the test where they're comparing signal and spatial resolution, usually they're inversely proportional. As one goes up, the other goes down. Signal goes up, spatial resolution goes down. Spatial resolution goes up, signal goes down. Spatial resolution. This is determined by our voxel size. And once again, the definition for spatial resolution is the ability to resolve one structure from another on our image. It's controlled by only 3 parameters, and we already mentioned them up here. Field of view, number of pixels, and then total number of pixels is your matrix size. So whether it is 272 by 272, that's your matrix size. But that also is the number of pixels that you have, total number of pixels. And remember, with matrix size, you can have a fine matrix. Sometimes they'll call that a larger matrix. And then you can also have a coarse matrix or a small matrix. So, depending on the wording, try not to get confused. A larger matrix means smaller pixels. A fine matrix means smaller pixels. A coarse matrix means larger pixels. A small matrix number means larger pixels. And then slice thickness. So these first 2 parameters really give us our pixel size. Then you multiply by a slice thickness, that gives us our voxel size. That's why our pixel size equation divided by phase encoding times field of view divided by frequency. And then to get voxel size, it's basically what we just had above times size.
That's voxel size or voxel volume?
Voxel volume. Yeah, that's a better way to put it. Voxel volume. But they might say voxel size on the registry. But the more appropriate way to say it is voxel volume. Everybody got that written down? All right. Here are all your S and R parameters that we talked about on those PowerPoint lectures, broken down into two subsets. You have hardware and contrast parameters. Our hardware parameters are really dealing with what type of magnet do we have? Do we have a 1.5 or a 3 Tesla? And then also, what type of coils do we have? We have the body coil within the scanner, but then do we have linear coils or do we have quadrature coils? Do we have a phase array coil? Do we have a good surface coil that we can put right on the body? So for this first one, we could say 3 Tesla equals increased S&R compared to a 1.5. Coil type, we could say quadrature or phased array equals increased S&R. Remember, the smaller the coil, the better the signal. The larger the coil, the more coverage you get. Remember, you have to lay that coil on the patient appropriately. To never put the coil at an angle. You always want it to be 90 degrees.
What's PA?
Phased array coil. Phased array. Remember, our spine coils are phased array coils. When we talk about pulse sequence, our spin echo will give us increased SNR. You could say compared to our gradient echo. And that's because our gradient echo lacks that 180 degree refocusing pulse. That's the most important thing to remember when we're talking about spin echo versus gradient echo. You'll always get more signal from our spin echo compared to our gradient echo because we have 180 degree refocusing pulse to boost that signal back up. And then you have your contrast parameters down here. TR, TE, flip angle. So as we increase TR, increase our signal. But that's up to a point. And the reason is, remember, our TR eventually plateaus off like that. So you'll see on the test, as we increase our TR up to a certain point, our signal increases. Because once it's hit 100%, or that tissue's fully recovered, it doesn't increase our signal anymore. The opposite is true for your TE. So as we increase our TE, right, we decrease our signal. That's because our TE curve looks like this. So as our TE increases, our signal goes down. So if we have a shorter TE, we have higher signal, but as our TE increases, our signal goes down. all the way to 0. And then our flip angle. What's the most important thing to remember about our flip angle? It's usually for spin echo, 90 degrees is the best flip angle. But we're not always working with a spin echo pulse sequence. So our flip angle to our Ernst angle is going to give us our best SNR. So our flip angle could be 20 degrees for gradient echo pulse sequence because that allows us our tissue to fully recover with a really short TR. So our Ernst angle is always going to give you your best signal depending on the recovery of that tissue and the TR that you have selected. Everybody got that written down?
Yes.
And then here's your voxel size and sampling. So we already talked about voxel volume. As that increases, our signal increases. As our NSA increases, remember noise is random. So we're not going to get a directly proportional increase in our signal. We have to, as our SNA increases, it's going to be the square root of NSA. So if NSA goes from 1 to 4, it's going to be the square root of 4, which is 2. That's what our signal increases by. That's because the noise is random coming from our patient. So it's going to be in a different place each time. Receiver bandwidth. That's when we're collecting the data. So if we have a narrow receiver bandwidth, we're going to have increased SNR. Because we're filtering out the noise which is on the periphery of our signal amplitude. And these next two are really dealing with our resolution, or our voxel size. So as our phase encodings go up, our signal goes down. Once again, it's inversely proportional. As our number of slices, not the slice thickness, goes up, our signal goes up. So number of phase encoding, increase. Number of phase encoding, decrease SNR. Increase number of slices, we're able to cover more area, we get more signal from all the hydrogen protons. So increase. If that said slice thickness, if our slice thickness goes up, our signal goes up. All right? And that is all incorporated into that last document for Tiffany and Kiara that we went over last time here, where we determine what happens to our signal and our resolution when we change these parameters. So this is on Canvas, but that basically sums up what we just went over. So use that chart as a guide. You can use this in clinic also. So as you mess with the parameters, keep this on you so you can have an idea of what it's going to do to your signal and your resolution. Because the techs are going to want to know this from you guys probably the most, because that's what we're going to be manipulating the most in clinic is our TR, our TE, number of slices, things like that. So if you have this on you in clinic, just kind of maybe print it out and put it like in your pocket guide. Just create a little notebook. This will be a good reference for you. Any questions before we compete our Kahoot games? All right, get your phones out. So we have 3 different cahoots. So you have opportunity to win one. I want everybody in this. All right. Half of you, 6. All right, come on. 7. Do it quick before it kicks the other people out. Keep going. Who's not in? 9. One more. There we go. All right, let's go. All right, parameters and trade-offs. So this one's dealing with S and R. So as TR increases, all these questions will be about S and R. All right. Static magnetic field, B sub 0. We go from a 1.5 to a 3 Tesla. Good. Ooh, split halfway down. So if, once again, if you're imaging an area like the pelvis, which has more of those hydrogen spins, you're going to get inherently more signal from those tissues. Coarse matrix. Coarse matrix means bigger voxels. Oh, most of you guys got that wrong. So coarse matrix, bigger voxels, more S and R. Good. Maybe correct. Our field of view is shrinking, but our matrix is staying the same size. SR decreases. Pixel volumes, pixel size is getting smaller. Concern here. We got about half and half. Each one. You got to think about it. We're thinking about signal, not resolution. Thinking about signal. So again, our pixels are getting smaller in dimension. And still consistently down the middle. Good. So not by a factor of 4 because it's the square root of 4, which is 2. So the answer is factor of 2. Our SNR decreases because our noise actually increases. So we get more blurring on our images with higher echo train length. So our SNR decreases. Arrow. See that we're filtering out. Good. It's false because T2 weighted have longer TEs than T1 in proton density. This goes back to our last unit on brain. SNR decreases, so our pixel dimensions are getting smaller. Phase encoding directions increasing. Square root. Smaller coil, better signal. Good. Inversely proportional. Last one. All right, let's see who won. Good job. Not very sure. I don't know what that second emoji is. Oh, their head's exploding. Good job, whoever that was.
It was me.
Oh, good job, Rachel. All right. So I have two others on here. We won't play them now, but I have one for resolution and scan time. And if you want my Kahoot password and practice these, feel free. I'll send that out. Okay. Do these help? Kahoots? Okay. We could always after break play the other two and then go over the brain. And it's a short unit. You want to do that? Let's take a 15 minutes. We'll come back at 7 or 10:35. We'll do the other two Kahoots and then we'll do our short lecture on pituitary gland. Online students. All right, so this next round, this one's on either resolution or scan time. Well, I'll see here. Game of Thrones fan.
Like the very first one.
What's that?
The very first emoji. I don't know what it is. Yeah.
They're just rolling their eyes.
Someone's excited. Oh, I know.
All right, we got 9. All right, so we can start with that. All right, so we finished signal. So now adjust your brain and think about resolution now. Resolution. Voxel size. Yeah, we didn't adjust our brains. So slice thickness increases, our voxel gets bigger, so our spatial resolution goes down. Just think about how, if the voxel gets bigger, your resolution goes down. It's the easiest way to think about it. Voxels once they get bigger. There we go. Steep gradients, so you're able to choose those more outer phase encoding steps so you get better resolution. Spatial resolution not effective. So somebody got that one. That was a kind of a trick question. So you're not filling some of those phase encoding steps, so your scan time goes down. Same resolution, should be the same signal, but your scan time goes down. All these were dealing with the voxel volume except for flipping. Oh, that's a contrast mechanism. Voxel volume, this equation. All sides equal. Good. All right. Congratulations. Whoever that might be. All right, little last Kahoot. This is going to be on scan time. So we can see that there's some areas we need to work on. So scan time. So think, there's three different equations. So just be mindful of that. One more. Scan time. Scan time. Switch gears. Scan time. Same equation. Gradient echo and spin echo. Fast spin echo. Forget to see this FSE. Fast spin echo. Good. Divided by echo train length. Volume acquisition. 3D volume. Good. Not the slice thickness, the number of slices. We didn't really talk about this. Echo planar imaging. Give it a shot. Pun intended.
That's what happened to me. My finger slipped and I put it on the wrong one.
My screen was going dim, so I hit it and it broke on something. I don't know.
So it's the number of shots, which is basically the phase encoding divided by.
That was a joke.
I got it right and I put shots.
Like
Give
number
it
of
a shot.
shots. Yeah,
Just
right.
say a shot.
So, there you go. Of course.
I just gave the answer.
Okay.
Phase encoding is divided by echo. 4 times as fast. There's no need to like divide it or anything. Just 8. Echo train length fills 8 lines of K space. It's going to be 8 times faster. Not affected. D is not part of the scan time equation. Trick questions come in. Somebody gave up. Once again, number of frequency cube, not part of the scan time equation. Double NSA, double scan time. Well, as long as you understand the concept, hopefully the app is just screwing up. Square root of 2. That's the answer. Double NSA, you do square root of 2, or whatever you increase your NSA, SNR. So this is a little different, not scan time, SNR. So just be mindful what they're asking. Good. No effect. 2D acquisition. Number of slices, not part of a 2D acquisition scan time equation. Good. Frequency, not part of the scan time equation. Field of view, not part of the scan time equation. No effect. Slice, number of slices, part of the 3D scan time equation. not slice thickness. Increases our scan. So reducing ETO increase. If we increase our ETO, we'll improve our scan time. Good. Just a different way of asking a trick question. Decreases our scan time. We're not filling as many of those phase encoding steps. They're there, but we're just not filling them. Good. Remember, case space is symmetrical. Fill the top, we can just basically invert the data into the bottom half. You'll see this on your scanner as iPad. Just another way to fill case space. Decrease your scan time. Good. All right. So you can see there's work to be done. So obviously you're a little rusty coming off the break. Review your PowerPoints. If you weren't here for that last lecture, both those PowerPoints and what we did last class are on YouTube. You can watch those. Make sure you review that Excel document. But you really just got to hone in on what they're asking. Are they asking about signal, or are they asking about spatial resolution? As your voxel size gets bigger, your signal goes up, your spatial resolution goes down. If you just have one concept kind of in your mind when you take this test, keep that concept in your mind. Or you can think of it as if your voxel size decreases, your signal goes down, but your spatial resolution goes up. And everything else is kind of incorporated around that concept. Okay? But there's definitely room for improvement. Make sure you guys are studying. Watch these videos over again if you need to. But you have all your resources on Canvas. Any questions?